Hi, this is Daniel W. from Mr. Happ's Period 2 Calc AB class, and today I'm going to be talking about the Calc AB 2007 FRQ number 1. And let me preface this by saying that the handwriting is going to be pretty bad because I'm writing on my computer using a mouse, and that this solution is going to require a graphing calculator that has calculus capabilities, but that should be a prerequisite if you are going to take this test. So let's jump straight in. Um, the question states, let R be the region in the first and second quadrants bounded above by the graph of y equals 20 over quantity 1 plus x squared, and below by the horizontal line y equals 2. Find the area of R. So it turns out you don't really need to know what this graph looks like in order to solve this problem, but it's always helpful to know what you're dealing with. So because we have a graphing calculator, we can just graph it and to see what we're dealing with. So let's graph both of our functions to see what our area R is going to look like. So because it's bounded above by this blue graph and below by this horizontal red line, it's going to be this area kind of in the upper middle section here that's above the red line and below this blue line. And notice that f1 of x does have a vertical asymptote at x equals 0, but because they do approach x equals 0, we can find an area using calculus. So it says to find the area of this section. So first we're going to have to find where these intersect so we can find the upper and lower bounds of our integral. And in order to do that, we're going to want to know when 20 over 1 plus x squared, when the y-coordinate of that is going to be 2 to find when they intersect. And that's pretty simple. We're just going to set 20 over 1 plus x squared equal to 2. We can divide both sides by 2, multiply this out of the denominator, and get 10 equals 1 plus x squared. X squared equals 9. X equals plus or minus 3. So that means that this point and this point are going to be -3 and 3 respectively, and those are going to be the lower and upper bounds of our integral. So let's actually go about solving part A, which says to find the area of R. So R is going to be this area, and to find the area of that, we're going to want to find the area under this blue part, which is going to be all of this, and then we're going to want to subtract the area that's under the red part, which is going to be this part down here, and that'll just leave us the area of R that we're looking for. So how do we do that? Well, we take our integral of our upper function, which is this, and then subtract our lower function, whose area we don't want, and we integrate that with respect to x. And notice that we can't perform this integral by hand, but this is on the calculator section of the AP test, so we can just plug these numbers into our calculator. As shown. Oops, minus 2 dx. So the calculator is going to give us an exact solution, but we don't want that. We want this. So we have that this integral is equal to 37.96, oops, 37.961 or 962. Doesn't really matter. So that's going to be the solution for part A. So part B asks to find the volume of the solid generated when our region is rotated around the x-axis. So it's asking when this region is rotated around the x-axis, what's the volume? So we should remember that the volume of this region rotated around the x-axis is going to equal the volume of this whole region that's under F1 when that's rotated around the x-axis, minus when this bottom area, F2, is rotated around the x-axis, and it's going to leave us with just the volume that we want. So it's kind of the same idea as part A, except it deals with volumes instead of areas. So our formula that we're going to have to remember is pi times the integral from our lower bound to our upper bound of our outer radius squared minus our inner radius squared. So our outer radius is going to be 20 over 1 plus x squared, and then our inner radius is going to be 2 squared, which we know is 4, and then we're integrating that with respect to x. So we can't do this by hand, obviously, so let's input it into our calculator. And we're going to skip by our exact solution and get that this is equal to 1,871.19. So that's going to be the volume. It doesn't ask for units, but we can just put units cubed or whatever, and that's going to be our solution for part B. Part C asks us to find the volume of our solid if this region R, which is this, is used as the base of a solid whose cross sections perpendicular to the x-axis are semicircles. So that just means that we can find the volume using a formula that hopefully we remembered in class, but if not, you can derive it on your own. So if the cross sections perpendicular to the x-axis are semicircles, the formula is pi over 8 times your integral from a to b of your radius squared with respect to x. So what's going to be our radius in this problem? Well, our radius is going to be the distance between this graph and this graph, which is actually just going to be 20 over 1 plus x squared minus 2. So pi over 8 times the integral from -3 to 3 of 20 over 1 plus x squared minus 2, and that's all going to be squared dx. So yeah, we're just going to input this into our calculator. So pi over 8 times the integral, oops, and that's going to leave us with our solution, which is 174.268. Oops, 8. So that's the FRQ, and if you think that you need a little bit of extra help with this, or with these types of free response questions, chapter 9, chapter 9 of your early transcendentals textbook is going to be really useful. I think it's called Applications of Integration, and it does go over all of these things. So I hope that's helpful.